Okay, hello and welcome back everyone. Moving on to section 3.3, we're talking about the implicit function theorems and the inverse function theorem. It really is two subsections, but they're so closely related to each other that it's nice to group them together into a single topic. So we'll start with the implicit function theorem. And you've probably worked with implicit functions in the past, but maybe didn't really know that that's what you were working with at the time. Right, in Calculus 1, you definitely spent a section on something called implicit differentiation. And you would start with expressions like y squared plus xy minus 2x squared equals 6, and you were asked to find dy dx. And maybe the way you would do this is you acted d dx on the entire expression. Of course, d dx on the 6 on the right-hand side will just give you a 0, but you acted d dx on the entire expression. You use your derivative rule, so we'd have a chain rule right away to give us 2y dy dx. And then there was a product rule, so you'd have d dx on x, which is just one copy of y, plus x times dy dx. And then maybe you took a derivative of negative 2x squared to get negative 4x. And then because d dx on x is 1, there's no chain rule from that term. And then you'd be asked to algebraically solve for this expression, dy dx. So you bring everything that's not with the dy dx to the right-hand side and keep everything with dy dx on the left. So that gives you 2y dy dx on the left plus x dy dx on the left. Then on the right, you'll have, I guess, positive 4x minus y. And then to solve for dy dx, you would factor it out to the right. So dy dx factors out. We have 2y plus x left over, and this is equal to 4x minus y. And finally, we divide both sides by the coefficient 2y plus x and divide by 2y plus x. Canceling on the left, and we find out that dy dx is equal to 4x minus y divided by 2y plus x. And so this was your experience with implicit functions so far. In multivariable calculus, of course, there's higher dimensional versions of everything we just did. But in fact, we kind of focus on the definition of implicit function a little bit more deeply. It's a little unclear in Calculus 1 why these objects should even be considered as functions. You would often use implicit differentiation with related rates problems and never really consider them as functions themselves. So today we'll finally kind of tackle what it means for an expression to actually define an implicit function. And then we do have kind of our multivariable version of the implicit differentiation, where you can find some derivatives of implicit functions. So let's think about a curve. One-dimensional object embedded in two dimensions for now. So we've got a curve, maybe not representable by a function. A classic example would be the unit circle. And below I've got the unit circle. Why is this curve not representable by a function, at least in terms of f of x, is defined to be some expression of x. Why isn't this a function? Well, it doesn't pass the vertical line test, right? We would learn this vertical line test, at least when we plot functions, probably in middle or high school, that all functions have to pass a vertical line test. And so we basically have no hope of writing this curve as a function in the way it's represented here. However, there is kind of some version of an implicit function that we can use to represent the curve, right? X squared plus y squared equals 1 is, of course, a collection of x comma y points, which satisfies this equation, and if we plot all solutions, we get exactly the unit circle. And so you kind of discover this, right? If I just decided to say, hey, here is an equation of two variables, x and y, solve the equation for y, you could do that just fine. You find out y is plus or minus the square root of 1 minus x squared. But this plus or minus is a pretty big deal. The plus or minus means that there is not a unique expression for y, right? Not unique. So because I have this plus minus sign in the middle, we actually don't know, is y equal to the positive square root or is y equal to the negative square root. There's just not an answer, and that means that y can't be a function of x because functions require unique outputs. Similarly, we could have also asked the equivalent question, can we solve it for x? And we would also encounter a plus minus in front of the square root sign. So there's really no way to uniquely solve one variable in terms of the other. So what do we do then? What we do is we restrict the region of a given curve so that the vertical, or possibly horizontal if we're looking for x as a function of y, but in this case, so that the vertical line test actually is satisfied. Notice I just deleted the lower half of the unit circle, and the price I paid to delete it is that no longer am I working with x squared plus y squared equals 1, but I'm working with the additional requirement that y is greater than or equal to 0. So sometimes we just have to add a little bit of extra constraints into our problem, and then we are allowed to write one variable as a function of the other. Of course, in terms of the upper semicircle, which is what I left there, we just choose the positive of the plus or minus sign that we would end up with. And now this expression, right, y equals root 1 minus x squared, is y as a function of x. And so we've moved our way from an expression, or an equation in fact, into a function by restricting some specific values that the xy points could obtain. This is what the implicit function theorem is going to build for us. It's going to tell us in what sorts of situations we will or will not be able to uniquely solve one of the variables of an expression or an equation in terms of the rest of the variables. That will be an implicit function, right? This would be an implicit function. It's always an implicit expression, always, but an implicit function when one variable can be uniquely solved for in terms of the others. And it's that unique that's very important for implicit functions. So what does the theorem actually say? Well, I do have to extend our notion of this circle to any number of dimensions, which makes our life a little bit ugly in terms of stating, but I'm going to try to make things as pretty as possible. So think about this f of xy, think about it in our circle example as x squared plus y squared minus 1, because of course if that's equal to 0, you get the circle of radius 1. So that's going to be like f of xy, and then this thing's always equal to 0. So you have some expression of x's and y's that are always equal to 0, but I've bolded the x and the y here to kind of refer to the fact that they can exist in any number of dimensions I want. So this could really be something like f of x1, x2, x3, comma, y1, comma, y2 equals 0. And in fact, the output here, right, f is also bolded, so everything is multidimensional in outputs potentially. So you have this like big function equal to 0. It's representing some system of equations that defines a set of points that satisfy that system of equations. We call these points x comma y, and they occupy some higher dimensional space. The implicit function theorem says, let's consider one specific point which we know solves the system, meaning that it actually is a point that solves the system we care about. And then we're going to ask if there is a region around the point. Big question, is there a, I'll put in quotes, small region around this point for which the vector y, or the multidimensional point y, can be solved uniquely for in terms of the multidimensional x's. Big question, can you uniquely solve for the variable y in terms of the variable x within some region of the point that I care about? So I'm going to head back up really quickly to the unit circle and try to describe what I'm saying. In terms of the upper half unit circle, this is kind of the useful point. This is a point which we know satisfies x squared plus y squared minus 1 equals 0. In fact, what is that point? 0 comma 1. Within a small region around this point, so like here, the question is, can you solve for y in terms of x? And the answer is yes. Within that region, you can say that y is equal to positive root 1 minus x squared. So it's possible to solve for y in terms of x within a small enough region. Now we know that this region in fact extends all the way out to here and all the way out to here, because we can actually see the entire plot and decide where the vertical line test fails. That's not what the implicit function theorem is telling us. The implicit function theorem is telling us that there exists at least one region. It doesn't tell us how large the region is, but it tells us there is some region around a point we care about within which you can uniquely solve for one variable in terms of the others. And what do we need to do to verify or to make sure that you can uniquely solve? Well, what you need is the derivative of your function just in the y variables. So the total derivative, but it's really total in the y variables, derivative of f to be an invertible matrix. So as long as you take the total derivative of f in terms of all of the y variables, you don't worry about the x variables, just the y variables. As long as that's an invertible matrix, then you can do exactly what I was talking about. You can solve for the variable y as an expression involving the variables in x. Now, what is that total derivative just in the variables y? That's what I've described here. So you think about it, you fix the point, the input to that special point, you just fix it for x, and you consider y now as the only variable that's allowed, and then you take a derivative of that multidimensional function, right? It's just restricting to only the variables y, and then you evaluate at this point that we care about. And as long as the total derivative in those y variables is invertible, then you can solve for the variable y as an expression involving the variables of x. Now, in fact, the implicit function theorem can tell us one extra tiny little bit of information. And the tiny little bit of information it tells us is this is the equivalent of implicit differentiation. In fact, it tells us what the total derivative of this function is, right? This is now itself a multi-dimensional function, and we can learn about the total derivative of that function specifically at the input x0. This is the input of the point, the x value of the point I care about. It says that that total derivative will always be the negative inverted total derivative, the one that I needed to guarantee existed. It's the negative of that inverse. And then that inverse acts on kind of the reverse. This is the total derivative in the x direction of the function I started with. And so you get this very interesting property of like the inverse derivative in y directions multiplied by or times the derivative in the x directions. And there's a negative, right? It's a negative. That's what you end up getting as our implicit differentiation. It's the negative inverse derivative in the y directions times the forward inverse in the x directions. So how does this really get used? Well, we'll just do this unit circle one, right? Go back to the unit circle we started with, and I kind of already mentioned that the unit circle's implicit function is this one, x squared plus y squared minus 1 equals 0. That's the implicit function that defines the unit circle. And so we ask ourselves the question, given some point, and I'm going to refer to exactly the point I cared about earlier. So here's my unit circle, and I'm going to isolate the point up here, 0, 1. So I take a point that I know is on the unit circle. I have a question. My big question is the system of one equations locally uniquely solvable for the variable y within a small enough region around the point 0, 1? So is there a region in which I can uniquely solve this equation for the variable y around this point 0, 1? All we do, I mean, we know we can because we already saw we could, but imagine that we didn't know that we could. All we have to do is we have to take a derivative of this function in the variable y. So we're going to do a derivative in the variable y, which of course I can represent as like the total derivative in the variable y of my function, but you know, there's only one y variable here, so in fact this is the partial derivative in the variable y of my function. I take a partial derivative in the variable y of x squared plus y squared minus 1, I end up with 2y. And then I ask myself, considered as a matrix, right, 2y should be considered as a matrix here, is 2y invertible? So I say is 2y, which is my, this total derivative in the y variables, invertible as a matrix at the point 0, 1. Well, 0 is the x input, so I'm going to plug in 0 for x here, but of course there is no x there. 1 is the y input, so I'm going to plug a 1 in for y, and when I plug a 1 in for y, I get 2 times 1, which is equal to 2. Is 2 invertible considered as a matrix? Of course, the inverse of 2 considered as a matrix is 1/2. And so the inverse exists, which means the answer is yes, you can solve for my expression uniquely in terms of y in some region around the point 0, 1. I can then actually go one step further, and I can say, okay, given that solving for y as a function of x, what is y prime, what is the derivative y prime of x at that point? Right, so if I were to actually solve it as y as a function of x, what is y prime, or equivalently dy dx, at that point? Well, we know from our unit circle, I'm just going to draw the unit circle again and look at our special point here. What is, if I have a function of y there, what is y prime? Well, it's the slope of the tangent line there. Slope of the tangent line 0. So I know I should get 0 as my value, but does the implicit function theorem also tell me that the answer is 0? And let's just go back to the theorem really quick and see what it tells me, how I can compute this derivative. It says the derivative of y as a function of x is the negative. It's that inverse that I just computed to verify that the inverse could exist. And then I'm going to multiply that by the derivative in the x directions also evaluated at the point. So recall the inverse I just computed was 1/2. So I've got my 1/2 here. There's a negative that shows up in front of that inverse. And then I'm going to go ahead and compute the derivative in the x directions, right? This is dx of f, and then I evaluate at the point I care about. What is partial x of x squared plus y squared minus 1? This is 2x. If I take 2x and evaluate at the point, I just get 2 times 0. So we find out the derivative of y, or y prime at 0, 0 being the input, is 0, meaning it's got a flat tangent line there. And that is standard implicit differentiation kind of from a different perspective. You could find out that if you apply all of these rules to implicit differentiation that you had in Calculus 1, you would get the same answers. But this gives us the ability to do it with total derivatives in much more high dimension. Now I do have a remark here that's pretty important to internalize. This remark says that the implicit function theorem will not actually produce that explicit construction of the function that it's describing. So the implicit function theorem is only telling me it's possible to write y as a function of x. It's not going to tell me how to do it, which I think is kind of interesting. It's just going to tell me if it's possible. It will also tell me about the value of the function there and its derivative, but it won't tell me anything else about the function if I could explicitly compute it. So sometimes it's actually quite hard to specifically compute the rearrangement that the implicit function theorem says is possible. It's more useful that we just use the implicit function theorem to produce the derivative at a given location, the same way that we used implicit differentiation to give us a derivative at a location. So here I've got a nice example of the implicit function theorem in higher dimensions. So you can start to see how this might work in an arbitrarily large setting. Now, unfortunately, we lose any visual understanding of what's happening in higher dimensions, right? In our two-dimensional case, which was really a one-dimensional function embedded in 2 dimensions, it was quite clear that the implicit function theorem was referring to locations on the unit circle where within regions of which I could solve for y in terms of x. Now we have to do that, but we do it without a picture. And so what we have instead here is we just have a system of 2 equations with 4 unknowns. We've got x plus y plus z plus w equals 0. That's a hyperplane. And then we've got x squared plus y squared plus z squared plus w squared equals 2. And that is a hypersphere. And so if we're going to satisfy both equations at the same time, we are really describing the intersection of a hyperplane with a hypersphere, both really 3-dimensional objects embedded in 4 dimensions. So there's no way to think about what this might look like as a set. And yet we can still ask quite interesting questions about functions. This would be useful if you were trying to optimize a situation subject to the locations on this intersection, such as in the last video. You would want to know if there is a region of 4-dimensional space within which the intersection of these 2 sets can be represented as a function. And in fact, in this case, a function of x and y is what I'm asking. So can I rewrite this system of 2 equations with 4 unknowns as really a z of x comma y and w of x comma y equals just expressions of x and y in both cases? Is that even a possible thing to do? And the implicit function theorem is what tells us if it's possible. So what we do need in a case like this, we will need to identify a couple things. We'll have to identify a point which actually satisfies the original system of equations. So I'll need a point that we're trying to kind of invert the function at, or at least write the function as a z in terms of x and y and w in terms of x and y. So we'll need some point that we can do it at. And hopefully that point, when we take the restricted derivative just in the variables z and w, because those are the variables we're trying to solve for, hopefully the restricted derivative in those variables is an invertible matrix. So let's start by finding a point which satisfies the original system of equations. Now this may seem really daunting, but in fact, because we have 4 variables and only 2 equations, odds are pretty likely there's more than enough freedom to find points which satisfy these equations. In fact, so much freedom that we can just decide to choose values. This is just an arbitrary choice to see if I can find z and w, which will work. So I've just arbitrarily chosen 0 for x and y. because I know that there's enough space in this intersection that I will be able to find a z and w. So I've just chosen them to be equal to 0 and make my system of equations as easy as possible. So just force those x's and y's to be 0, and now our system of equations reduces to a system of two equations with two unknowns, where the first equation, z plus w equals 0, just tells me that z is negative w. And once I know z is negative w, I plug that into the second equation. So I plug negative w in for z in the second equation. We find out 2w squared is 2, so then w just has to be plus or minus 1. And in the event we choose maybe negative 1 for w, we find out that z, which is negative w, is positive 1. So at the very least, we've isolated this point, 0, 0, 1, negative 1, as one possible solution to my system of equations. But of course, there are infinitely many more. To answer our question, though, we just need one. We just need to find any point which satisfies the original system. And then now we will have to go through this extra bit of work to see if this restricted derivative as a 2 by 2 matrix is invertible at that point. So to do that, we'll have to go ahead and compute the restricted derivative of our function. And so keep in mind that the system we originally started out with, that was equal to 0, that was equal to 2. As long as the right-hand side is equal to constants, you just don't want any variables on the left-hand side, you can just extract your function as the terms with all of the variables in it. And so that's going to be my function of 4 inputs and 2 outputs. I'm going to compute the restricted derivative of my function at the point 0, 0, 1, negative 1, and specifically because I only need the restricted derivative in the variables z and w, I can just go ahead and take those x and y coordinates and plug them right into the function before I get started. That makes my life easy because now I can think about this. I can think about this as a function with 2 inputs and 2 outputs. And that's good because that'll give me a square matrix when I take its derivative, meaning we'll have a chance to get an invertible matrix. So at this point, I'm just going to compute the derivative of that function, right? This function of z and w. And let's just recall I'm doing partial z in my first column. So partial z on z plus w is 1, and partial z on z squared plus w squared is 2z. And I'm going to do partial w on my second column. Partial w on w is 1, and partial w on w squared is 2w. So that will give me my total derivative restricted to the variables z and w, and then I will have to evaluate them at the point that I care about, where z is equal to 1 and w is equal to negative 1. So that's going to give me the matrix 1, 1, 2, negative 2. Is that an invertible matrix? Yes, it is. We just go ahead and use our 2 by 2 inverse formula to verify that the invertible matrix does exist. So once we've done that, we have actually established the two things we need to say that yes, you can definitely solve for the variables z and w in terms of the variables x and y, at least within a region, right? There's a small enough region around this point in R4 that you can solve for z and w in terms of x and y. Now we could go farther, right? We can go farther with the formula, and the formula can tell us what the derivative of this function, right? The total derivative of this function g would be. The formula says that the total derivative of g as a function would have to be negative this restricted derivative in the z and w coordinates of f, inverse, and then the restricted derivative in the x and y coordinates of f, right? You would multiply all those together to find kind of the total derivative of g specifically at that point. But that's not really what we were looking for here. We just wanted to know whether it was even possible to write z and w in terms of x and y. And what we learned was, yes, it is possible. So that's what the implicit function theorem can do for us sometimes. And it's got a sister. The sister of the implicit function theorem is the inverse function theorem. And they're going to feel the same the whole time, but they are trying to poke at very slightly different things. The inverse function theorem is kind of trying to tell us when equations themselves are solvable if we modify some of the parameters in the equation, where the implicit function theorem is telling us when we can rearrange systems of equations for specific variables. So there's very slight, subtle differences, but they are corollaries of one another, right? And once you have an inverse function theorem, you have an implicit function theorem. Once you have an implicit function theorem, you also have an inverse function theorem. So there's not really anything too special about one versus the other, but I will just jump ahead. I have a good discussion there if you want to read it, but I will just jump ahead to what the inverse function theorem actually says, and things are going to look a little bit familiar here. So with the inverse function theorem, we're just going to start with a function whose input space and output space are the same size. And when we take that function, and we take a total derivative of the function at a specific point, if the inverse of that total derivative exists, then we know that the inverse also exists, at least in a small region around that point. And this is where everything is starting to feel somewhat similar, right? We're still isolating a specific point. We're still testing whether or not the derivative of a function is invertible as a matrix. And then we're still claiming that you can then write some explicit expression as a function. In this case, that expression we care about is the inverse function. So really just think about the inverse function theorem as stating a local inverse exists if the inverse of the derivative, right? And those are two separate operations. You compute the derivative first and then an inverse second. The inverse of the derivative exists. That's what the inverse function theorem is saying. This actually makes a lot of sense, even going back to calculus 1. Where would you find out a function isn't invertible? You would find out a function is not invertible when it fails the horizontal line test. And a function fails the horizontal line test specifically when the derivative of the function is equal to 0. So when the derivative of a function equals 0, we fail the horizontal line test. I mean, maybe not always, but it's at least enough to not guarantee that we pass the horizontal line test. And so the function is not necessarily invertible there. Sometimes it is still invertible, but other times it's not. And of course, if the derivative of a function is equal to 0, then the inverse, really the reciprocal of 0 is undefined, right? 1 divided by 0 is undefined. And so we do see kind of the same sort of shape happening in calculus 1 cases. This is the more complicated situation. And just like the implicit function theorem, the inverse function theorem will tell us about the value of the derivative of the inverse function. So notice very carefully where I put my brackets on these, because there are going to be times where I'm computing a derivative of a function at a point, then I'm closing brackets around it because that's been computed as the derivative of a function at a point, and then this inverse that's coming afterwards is referring to an inverse matrix, whereas on the left-hand side here, this is really referring to the derivative of the inverse function itself. Okay, so the inverse is happening on the function first, and then I'm computing a derivative. But what this theorem says, finally, in one final step, is that if I take the derivative of the inverse function and evaluate on the forward function at the point, that's always going to be equal to the inverse of the derivative of the function evaluated at the point. Anyway, that's what the inverse function theorem says. It's telling you when an inverse function actually exists. And if we're going to apply it, we can apply it in the following setting. We often apply it to try to talk about solutions to systems of equations. And so the big question here is we've got this system of two equations and two unknowns defined by x squared plus x cubed y cubed is equal to 2. And then the second equation, y squared minus x cubed y cubed is equal to 0. We don't necessarily ask questions about does this set of equations have solutions, because in fact we see that it does have solutions here. There are 4 of them here. And we see at least one of those solutions does occur at 1, 1 in r squared. That's not actually what we're curious about. What we're curious about is kind of how much wiggle room do we have so that we maintain the existence of solutions. Here's the big question. How much wiggle room do we have so that we maintain the existence of solutions? What do I mean by wiggle room? Well, if I took this curve and I started pulling it to the left, and I took that curve and I started pulling it to the right, eventually those curves are going to stop overlapping, and I'll no longer have a solution, at least in that top right quadrant. So there will be a point at which these were strings and I were pulling on the strings, that the strings no longer overlap. And so the question is, do I have wiggle room, and how much wiggle room do I actually have? Well, what we do here to kind of represent that wiggle room, there's lots of ways you can wiggle these expressions, but the way we've chosen is just to add epsilon to the right-hand side of both. And the big question is, would there still be a solution to my system of equations given some small epsilon here? All right, if I keep epsilon somewhat small, do I still maintain solutions? The inverse function theorem is going to tell me that the answer is yes, so long as the total derivative evaluated at the solution I already know, so solution to original equation, right, without any epsilons on it. So if that function has an inverse, in other words, does the derivative have at the point have an inverse matrix, then the answer is yes. And so to verify whether or not this is possible here, we just once again take the entire left-hand side and consider it as a function of two variables. And then we're going to compute its total derivative, where of course I'm doing the partial x of the entire function on the left, which gives me 2x plus 3x squared y cubed, as well as negative 3x squared y cubed. I'm going to do partial y on the right side of my total derivative. I'll get 3x cubed y squared and 2y minus 3x cubed y squared. And I care specifically about the value of this total derivative at the solution I already know, which is at the point 1 for x and 1 for y. So when I plug a 1 in for x and y in my total derivative, I get the matrix 5, 3, negative 1. Does the inverse of this derivative exist? The answer is yes, because I compute a determinant. When I compute the determinant, I get 4 as the determinant. So since the determinant is non-zero, the inverse exists. And now the inverse function theorem says, hey, f inverse exists at least within a small enough region near the point 2, 0. What do I mean by that point 2, 0? I mean, here's the point 2, 0, right? If I'm considering the left-hand side as a function and the right-hand side as the image of the function, I care about the inverse function acting on the point in the image, acting on 2, 0. So it says that the inverse function is well defined near the point 2, 0, and so f inverse of something like 2 plus epsilon, and epsilon, at least for small epsilon, is still going to be well defined, and the output of this function would be some x, y, which solves the modified system. And below, what I've shown is I've actually chosen some values of epsilon here. If I let epsilon be negative 0.05, that's me tugging on these strings a little bit, and we still maintain solutions because those strings are overlapping a little bit, but even something like epsilon being negative 0.2, all of a sudden the strings are no longer overlapping. And so you get this notion of, yeah, small enough epsilon will maintain solutions, but a little bit larger will not. But you know, that maintaining solutions kind of really corresponds to like how much space this determinant has before it reaches 0. Once the determinant becomes 0, in fact, that's the point at which the two curves here are only intersecting at a single point. And once you go any farther than that, then there's no longer going to be any solutions. So that's really how we would use the inverse function theorem. It's a very fun section that we've covered. Lots of intense stuff, right, with those restricted derivatives and really thinking in higher dimensions in a way maybe we haven't thought of before. But we are trying to solve systems of higher dimensional equations, and that is not an easy thing to do. So that's why these statements do look so complicated. Anyway, I think it gets a little easier in the next section. We're going to be wrapping up the chapter with divergence, curl, and the Jacobian matrix. See you later. Bye.